Okay, in this video, we will see a new architecture called transformers. It's a relatively recent architecture that has monopolized the last few years spaces like natural language processing, computer vision, and others. In this kind of architecture, we're going to start by connecting it to what we have discussed already, the context-free embeddings, such as, let's say, Word2Vec, and understand how this kind of architecture can actually generate inside it representations that are called contextual representations. And these are actually quite important because at the end of the day, you will actually can attach to those contextual representations downstream tasks or upstream tasks, depends on how you see it. And these kind of tasks like classification and others are going to sort of have significantly better performance as compared to what other architectures we have seen already. And also at the same time, they will actually offer some kind of a general kind of multi-model capability. And so we will try to dissect this kind of architecture in steps. Let's start by, first of all, sort of writing down and start doing the connection with the context-free embeddings I've seen in the past. Effectively addressing here transformers. And the first thing I want to kind of draw here is where actually we left it. Last time we talked about Word2Vec. And if you remember, we were dealing with this kind of a three-dimensional kind of a space. Let's call this for drawing this easily kind of 3 dimensions. This small letter D that we have talked about is 3 now. And we actually, what we saw is that a word, let's say the word bank, is mapped into this kind of 3-dimensional space at a specific point. And this is obviously what we call this contextual 3 representation, because there is absolutely one and only one kind of point in space, no matter what the underlying semantic of the word of the token bank is. So, for example, if it is refers to a river or refers to the financial institution, there's only one point in space. And what we will actually migrate towards to is, again, in this kind of a simple 3-dimensional kind of space, we will migrate to a situation where the word bank, if it is refers to the river bank, is going to be in this point in space. And if it refers, let's say, to the financial institution, it will actually be in a different point in space. So that's called contextual representation. And this is what the context is here is effectively, as you can understand, the context surrounding this kind of token. So if the context is that of National Geographic, then it will be on the green point. If it is context is around money, this also will actually make this same token map into the green point over there. So let's see how this will actually be done. So we will start with just kind of briefly reviewing the so-called task that we will be concerned with here. So we will sort of present this kind of contextual embeddings from a point of view of a task. So let's call this task the simple language model. It's called language. We have seen this task already implemented with other architectures, earlier architectures like recurrent neural networks in another kind of video, but the equation is actually identical. So we are after a conditional probability distribution typically we call these conditional probability distributions of the modeling exercise P model. For those who have not reviewed yet basics of statistical learning theory and understand what the P model is versus P data hat, I suggest that you also go back in that kind of introductory kind of videos and watch them. So this is WT given P, WT minus 1, WT minus 2, dot, dot, dot. WT minus N, let's say. So we are actually going back N points in time, where effectively it's the sequence of tokens that is kind of already we have seen already, and this is what we will call the context. So this context is of, let's say, N tokens right now, is going to be used to determine the next token, which is WT in this case. And in terms of kind of a topology, this kind of language model, which actually could be quite large, that's why I call it large language models these days, or LLMs, are actually sitting at the sort of bottom of this kind of pyramid, if I may call it, or stack. So this is the so-called prediction problem. So LLM will actually solve the prediction problem, which is basically is the next token prediction. And this has to be fairly accurate. Having said that, these days people are using applications such as ChatGPT and others who are effectively solving the so-called Q&A, or question and answer LLM problem. And this Q&A problem involves processing the predictions further, and involves in many instances reinforcement learning, either with humans or with some other ways, to make the model effectively perform best in questions that people have. It could be tasks, it could be some associated with coding, it could be a task, a question associated with some other domain. The Q&A model is what mostly people are actually using as part of these applications. And we will see though in a kind of another video. So in this kind of video, we will be focusing entirely on this kind of prediction LLM and trying to understand, if you like, the transformer architecture. And then on top of this Q&A kind of LLMs, we have the so-called agents that are actually could be fed by a Q&A LLM. So the agent's actually solving a much more general kind of task. It may involve other agents which are specialized in some specific type of questions, in some specific domains. They're actually using tools because obviously during the training of this prediction LLM, many things may have happened. So they're able to retrieve, let's say, the current news and respond back with answers associated with data and events that actually happened past this kind of a training cutoff date. So this kind of agent is also something that we will see in a kind of another kind of video. And this is mostly today agents are being used heavily in coding. So the so-called coding agents are probably 99% of the traffic associated with agents today on the AI space, and probably for a good reason. Okay, so as I said, we are just going to focus our discussion right now here. So let me just start the discussion by expanding a little bit this prediction kind of LLM based on this kind of transformer architecture into two parts. The first part is going to be associated with the so-called the attention mechanism. Which is probably the most important part of the architecture to understand and get it right. And as input to this, so I'm actually presenting a bottom-up approach where the input is at the bottom. We're actually going to see that we are going to have this kind of capital X tensor. This capital X tensor is going to sort of contain the input tokens of our context. And this attention mechanism is going to feed what we actually call the, I will call it the raw compute subsystem. It's a kind of a neural network that we have seen in the past called multi-layer kind of perceptrons, but it could actually be a bit more general than just NLP. And this these two are actually coming together in order to provide, at the end of the day, the contextual representations and the prediction towards the task that we have already have seen already in this equation, the prediction of the token WT. Okay, so the attention mechanism, which is the first part that we're going to discuss, is primarily responsible for what I just plotted a bit earlier, this kind of transition from a contextual free representation of the token bank into the contextual representations of the token bank. All right, so so the attention mechanism, let me just write it here as the first point of discussion. The attention mechanism is going to be introduced by looking at kind of three sentences. So the first sentence is sentence, I love bears. The second sentence is she bears the pain and bears won the game. So as you can actually see here, I'm just going to focus the discussion to the token bears. Bears in this case is definitely has some kind of affiliation with the animal bears. In the second sentence, bears is associated with probably the semantic of tolerance, meaning of tolerance. And in the third sentence, for those who are not familiar with US sports, bears is associated with the sports team. There should be a sports team always called bears anyway. All right, so as you can understand, the need for doing this kind of mapping from a contextual free representation of the token bears to three different points in a space is quite important to extract the right meaning of a sentence and actually perform well in other downstream tasks. So what we actually also can actually notice here is that something we have seen in the past, in that in each kind of sentence, the contextual kind of tokens, so out of just the three tokens in the first sentence, probably the token love is primarily responsible for kind of providing the right meaning to the token bears. In the second sentence, probably the pain is associated with that kind of role, providing that kind of meaning to the token bears there. And then probably both tokens, both won and game, are responsible in the third sentence to associate bears with the sports team. So what we can actually intuitively kind of understand here is that we need to definitely have a structure, what I called earlier this kind of a tensor capital matrix X, that kind of brings together the context that we have at our input. And the dimensions of this kind of matrix are going to be D columns, and we're going to have capital T rows. Okay, so capital T is the context size. So T is the context size. And obviously D, we have seen this many times before, is the typical letter that we associate with the dimensionality of the embedding space. All right, so for the purpose of this kind of discussion, because we kind of just like to kind of draw things here and have the sort of ability to follow numerically what's happening, so I am going to associate very, very small numbers to these tokens. And so the first kind of number is 4. So I'm just going to have 4 dimensions in my embedding space and just 3 tokens for my context. So as we just discussed, we would like to have a mechanism where love is going to affect bears and pain is going to affect the bears on the other sentence, and game and won bears on the third sentence, which means that we need to have some kind of a simple way that we have seen many times in the past to extract some form of relationship between vectors, because at the end of the day, all of these kind of tokens that we see here in kind of a natural language here, the machine kind of understands them as vectors at its input. It could be one-hot encoded vectors, could be vectors that are coming from word to vec. It doesn't really matter, but vectors, and we are going to just adopt the well-known to us dot product for this simple version of this attention mechanism that is going to calculate this dot product between X and X transpose, and this product between X and X transpose to form a matrix S that we will call the attention score matrix. So in terms of dimensions, as you can understand, this is T by D, and therefore this is D by T, making the S matrix a T by T, which, given the sizes of this matrix in practice, is a very significant matrix. It's like pretty large matrix, because T is in the order of many thousands, if not hundreds of thousands today, and or millions, and the D, the embedding spaces, also are pretty sizable. So we are going to sort of just basically plot it over here for the time, for the numbers that we have available to us. So we have effectively a 3 by 3 matrix here, because T is equal to 3 in our example. So if I write it down quickly, S33 here, these are called the attention scores. And obviously, as we remember from any dot product, these numbers here could be either positive or negative, because vectors may be pointing towards each other, vectors may be pointing opposite to each other, and therefore their dot products could be either positive or negative numbers. And what we will do is we want to have some kind of a ranking at the same time, which of the tokens of the context here is affected mostly by our current kind of content, how the context, delete. So what we want to see here is we want to get sort of an indication as to which of the tokens is affecting mostly other tokens, and vice versa. So we will adopt a well-known block for us to us. It's called softmax. We have seen this in the past. And back then we've seen it in a kind of a probabilistic kind of context, in a sense that we used it in order to convert a vector of logits, which are also the elements of that vector could be either positive or negative, first to all positive numbers, because inside the softmax there was this kind of exponent, and any number, either positive or negative, when it's exponentated, it is resulting into a positive number always. And and at the same time, it was actually by the normalization, by the denominator of this kind of softmax, it was providing for us a proper probability distribution at the end, where all the sums of all these kind of elements of this kind of vector at the output will be equal to 1. So similar things we would like here, but we don't have any probabilistic notion, at least not yet. We just use a softmax purely from the conversion to positive numbers and normalization, just to get at the end of the day a form of a ranked impact of tokens to each other. So what we have here is we have the output of the softmax is we call the so-called final attention weights. We call them weights instead of scores now. And again, this kind of attention weights are going to be definitely ranked, conveying effectively how much of that, how much of each token is affecting the other. So effectively, because of the softmax, we have the Aij is greater than or equal to 0. So all of these weights are positive numbers. And also at the end of the day, we have the very desired for us relationship that for the summation of across j's over the tokens of our context of Aij is equal to 1.0. Okay, so what does it mean? Is that if you see, if you like, the jth column. Okay, so if you look, sorry, at the row, so you have effectively here the summation of A11 plus A12 plus A13 is equal to 1. And you can actually see it also in terms of columns as well. It doesn't really matter how you express this kind of relationship. And so you can actually see that here we have token 1, 2, 3, token 1, 2, 3. So definitely we have an attention weight of how the token itself is potential affecting itself. That's why we call this mechanism self-attention mechanism. And we also have the numbers of how one is affecting token number 2 and token number 3. Okay, and so on for the others as well. And so we have a complete picture of who is able to affect each other. And I think it's a very instructive to also plot what is really going on here with this kind of self-attention mechanism. So I want to use this kind of a simplistic way of looking at things. So if I represent the contextual free representation of the ith token that I received in my input of this simple self-attention kind of mechanism, then what I have achieved at the end of the day is I have mapped this into another space in time via an equation which I will type in a moment. So xi became xi hat, and the mechanism, the simple self-attention mechanism, you can imagine it as acting, pulling this xi towards xi hat, and let's write it as simple self-attention. Okay, so what is the equation? What is this xi hat, and how we can actually write it now, now that we have this kind of weights? Well, simply the xi hat, let me actually write it down over here. Xi hat is equal to a summation from j is equal to 1 to t of Aij xj. So it's actually a linear operation. The way to see that also in terms of a vector form or matrix form, better, because we started with a matrix, is to write down the equation as x hat is softmax, effectively converting the block diagram we just drew, x transpose x. And if we associate the attention weight, we call it a matrix A. So this is effectively AX, which more than shows that it is a linear operation. So I'm going to stop here, and I'm just going to sort of what I'm going to do next is I am going to start discussing what is really the next step, because up to this moment in time, we just have a linear mapping, and we will need to understand first what motivates us to actually have now a non-linear mapping. So I'm going to stop the video, and I'll see you in the next video.